dioxide reacting with water will increase the concentration of hydrogen ions by that equation, will lower the pH, make it more acidic in that area, and you can get dilation of the blood vessels to let more blood flow into the area to wash away the carbon dioxide, deliver more oxygen. And adenosine and potassium can also contribute in a minor way to that. If the opposite happens and the amount of carbon dioxide in the extracellular fluid goes down, then that will reduce the amount of hydrogen ions or concentration of hydrogen ions in that area. pH will go up, in other words it will become more alkaline, and that will contract the blood vessels in the brain. So if you have reduced metabolism, the blood vessels in that area will contract by that mechanism. Now you can do this, you can actually do this on yourself, so anyone who's ever blown up an inflatable item, a large inflatable item manually, so if you've ever blown up a large balloon or an airbed or something like that with your mouth rather than a pump, you'll notice that you start to feel dizzy after a while and start to feel like you're going to pass out. That's because by hyperventilating you're removing carbon dioxide from your bloodstream and you're making all the blood vessels in your brain constrict. So blood flow to the brain is falling, and that's why you feel dizzy, because you've reduced the carbon dioxide in your cerebral blood flow, you've increased the pH, and that's making the blood vessels in your head contract, which is why you feel dizzy. So it's not a good idea to do that. It's a good idea to buy a pump. And as we said, people think the myogenic mechanism, so the effective pressure to make vessels constrict or dilate, causes autoregulation of blood flow in the brain. So that's all I had to say for today, and there's just a summary there of the lecture.
Can I quickly make an announcement? Is it okay? Hold on.
Now, I've got
I don't think they'll let you. Is it okay?
It'll be put up on the website today, so...
Hey guys! Hey guys, just a quick announcement that you know, we're recruiting for Medball subcommittee at the moment for 2010, so this is going to be the biggest social event of the year. So if you want to be in the subcommittee, if you're creative and you want to help us make posters, decorations, invitations, tickets, if you have a knack for computing skills, you can make videos good with Excel or organisation or enthusiastic. So give us a short blurb on what you can bring to Medball subcommittee to social@medsup.org.au. Thank you.
Oh, thank you. If you want, yeah, just leave it there.
Hi everyone. So tomorrow after lectures, GPSN is handing out their book thing that has lots of information. But we've also included a movie ticket and a couple of other cool free things in the book. So you know, grab one and maybe you'll win something. Yay! Cool.
Oh, it's alright.
Hey everyone, next Friday night is a charity cruise. Tickets are $50 and it includes drinks, unlimited pizza and a free after party. So it's called the Ruby Ball Cruise, and tickets will be sold from 12 till 2 on Monday to Friday outside the library. And yeah, it'll be great to see you all there. Alright, thanks.
Cool. Okay.
Yeah, so
That's all right. Oh, sure. Yeah, I'll do that. Okay, so you have to open it up. Oh, cool. Okay, excellent. Okay, thank you. Okay, we'll start. Okay, my name's Andrew Brown. I'm giving this lecture on fats, or as we like to call it in the business, lipids. Now, some of you will remember I gave a lecture on carbohydrates and lipids. Here we're really focusing on the lipid side. There'll be a couple of things in common, but a lot of it will be hopefully fresh to you. One of the things that I hope to do is to actually convince you that it was search of a particular type of lipid which brought our ancestors down from the trees. Hunting woolly mammoth. Okay, so basic things about lipids or fats. What they do, they provide essential fatty acids. What makes fatty acids essential? Don't speak with your mouth full. They're essential. They're essential. That's what you were trying to say. They're essential because we need them. We can't make them ourselves. That's what you're trying to say. I could see through the food coming out of your mouth. Okay, yeah, that's exactly the case. That's exactly the case. They provide concentrated food energy. So can you actually remember, and see if I've actually got it here, that fat is twice as energy dense as either carbohydrate or protein. So here we've got, I don't think my laser pointer is actually working all that well, but here we go. 37 kilojoules per gram for fat, 16 kilojoules per gram for carbohydrate. They carry fat-soluble vitamins. What are they? Which ones are they? Give me some letters. An A. B. No. Oh, D. D. And E. And fantastic. Okay, I've done my job. I can leave. A, D, E, and K. Yep. We'll talk briefly about those later. They provide that feeling of fullness. You know, when you've had a big fatty meal, you tend to feel either sick or satisfied, one of the two. And they slow gastric emptying as well. And indeed, this was published in Nature a couple of years ago. They're actually working out some of the biochemistry between that feeling of fullness, that there's actually that sensors in the intestine which can then relay that feeling of fullness to the brain. So the intestine actually has sensors for particular fatty acids or particular types of fatty acids, which then sends that signal through to the brain. Okay, what are fats doing in our body? Well, they're chief form of stored food in the body, serve as an emergency fuel in hard times, and the problem is that there really isn't a lot of hard time at the moment. And of course that's why we have the obesity epidemic. So that, they're fantastic for storing away our a storage form of fuel, but how many times is it between meals nowadays? If you're lucky, you might have sort of 8 or 10 hours at night. So something that you mightn't necessarily think of in terms of fat is that they protect our internal organs from shock. So they're acting like shock absorbers. They insulate against cold. How many whales have you seen which shiver? Not many. They've got all that blubber. Major component of cell membranes. Welcome to the lecture. Welcome to the lecture. I'm sure it'll be a very satisfying cup of coffee. Converted to other compounds on demand, and we'll have a couple of examples of that as we go through. Okay, so you had something like this in that previous lecture, but just to recap. So here we've got a steak that you might find in a butcher's. The white bit is the storage form of fat. Here we've got the nice muscle, and the cells of the muscle are going to have a membrane bilayer, and that's going to be a lot of phospholipid. So the storage form is going to be triglyceride. In the cells, the membrane form is mostly phospholipid. So triglycerides, very simplistically, here we've got a very simple structure for it. We've got a glycerol backbone. That's what glycerol looks like. Very simple, 3 carbons with hydroxyl groups. And esterified to those is 3 fatty acids, which is why it's called triglyceride or triacylglycerol. So 3 fatty acids. Ester linkage connecting the fatty acid and the glycerol backbone. So that's chemically how they're formed. So this is actually considered neutral chemically. So it's not polar by any stretch of the imagination. It's very non-polar, and it's the way that we store our lipids. It's the major type of lipid that we would be consuming in our diet. Phospholipids found in membranes, and they're polar. And what makes them polar is that just this phospho alcohol head group here. So that there's different types, and this is phosphorylcholine here. And so this is a phospholipid, phosphatidylcholine, also called lecithin. And I think you might remember that I might have asked you in the last lecture if anybody had a muesli bar or a chocolate. Does anybody have one here, which they haven't just consumed in the front row? No? No, everybody's, you've had your snack. Well, if you actually look at the wrapper and look at the contents, you'll actually see something. Okay, can you actually see the ingredients there? Can you see anything like lecithin there? Soybean lecithin, egg yolk lecithin?
Soy, almond, sulfites.
What? What is it? He's having the on.
Egg, cereals, milk, soy, almond, sulfites.
Oh, so it's not a complete sort of description. Oh no, that's probably just saying that if you've got a nut allergy, forget it. Does it say? Does it say lecithin? It says a lot. Okay. For the next lecture, it does. Excellent. I thought he was going to prove me a liar. Okay. So the lecithin here is making sure that the fat, which there's considerable amounts of fat in those muesli bars, chocolate bars, doesn't actually come out of solution. So you see this horrible, globby, visible fat. So the phospholipid is actually helping to solubilize that. And we'll actually see how that becomes important in helping to carry lipids around the bloodstream as well in the form of lipoproteins. We'll deal with that in the next lecture. Welcome to the lecture. Please come through. You missed out on all the best jokes. Yeah. That's all right. I'll make sure there's another good joke later on, just for you. Okay, so cholesterol and cholesterol ester. So this is what cholesterol looks like. 4-fused ring, aliphatic side chain here, hydroxyl group. So if you think about this, and I tried to impress this in that carbohydrate lipid lecture, that you can look at these molecules and sort of say, well, that looks pretty greasy. That looks pretty greasy because that's all hydrocarbon. The only thing which is giving it some polarity is this hydroxyl group there. And so this is hydrophilic, that's hydrophobic. When you've got a hydrophobic part and a hydrophilic part, do you want to just sort of quickly hand those around? The idea was that medical students are very organised and will have printed them out or have them on their laptop. And I can see a lot of people did that, but these were for the absent-minded medical student who obviously didn't get a chance to do that. Yeah. Okay. Anyway, let's if we can really take our places, that would be good because it's a bit disruptive if we're all sharing the floor. Okay, so that's is a property called amphipathic, which means that it veers literally both the polar hydrophobicity and hydrophobicity. So it's basically got both properties in the same molecule. Phospholipid is also amphipathic as well. Okay, and so here we've got a very simple diagram. Phospholipids, you can see their little sticks here represent the fatty acids. The polar head groups are the circular bits, and you can see the fatty acids actually point towards each other. They're both water-fearing, hydrophobic, and so they're pointing towards each other. The polar head groups can be in contact with the aqueous environment, either outside the cell or inside the cell. Okay, so that's how a lipid bilayer works, of course. So I'm sure I'm not telling you anything new here. And here you've got some cholesterol intercalated in that phospholipid membrane. Okay, so now we're going to spend a few moments talking about fatty acid nomenclature, types of fatty acids, and yeah, a little bit what they look like. So here we have, we basically talk about fatty acids in terms of how many double bonds they have. So I'm sure you've all heard of polyunsaturates. We'll come to those in a minute. Here we've got saturated fatty acids, which means that they've got no double bonds, no double bonds. Here is palmitic acid. The trivial names often come from where they were first found. So palm oil is a rich source of palmitic acid. It's got 16 carbons in length, so you can count each of these little joints here, which represent a carbon, and there should be 16 of them. This is the carboxylic acid group. So if you like, this is the fatty part, that's the acid part, which makes it the fatty acid. You can have longer versions, so this is with an extra couple of carbons, and it's stearic acid, as in steers, cattle, all that sort of stuff. And it's found in lard and also chocolate. Monounsaturated fatty acids. So here we've got one double bond, as suggested by the name, monounsaturated fatty acid. And here we've got palmitoleic acid, again 16 carbons in length, and that's what this represents, 16 carbons, colon, 1 for one double bond. And the delta 9 here means that that's the position of the double bond. And this is sort of the way that a chemist would talk about a fatty acid. always counting from the functional group here. So if you count 9 carbons along, you get to this first double bond here. Same with oleic acid, and oleic acid, olive oil. Lots of oleic acid and olive oil, but it's not the free fatty acid, it's actually esterified in the form of a triglyceride. Because plants like us store their lipids away as triglyceride. And so olive oil, when you're pouring olive oil in salad dressing, whatever, it's oleic acid but in the form of a triglyceride. Okay, so we have different sorts of unsaturated fatty acids. Mostly what we encounter in nature are called cis fatty acids. So the double bond is actually in a cis configuration, which I'll explain what that actually means chemically. But you will have heard of trans fatty acids as well. And so here we've got a feeble attempt from the fast food industry to sort of say we're doing the right thing, we're trying to get trans fatty acids out of fast foods. But believe me, there's a lot of trans fatty acids in processed foods. The reason being is that they use whatever is the cheapest oil for the fast food, and an oil by definition is liquid at room temperature, which isn't particularly useful in a hamburger or something fast food, because where you want it to be solid at room temperature. And so you actually have to start getting rid of those double bonds. The way that you do it chemically is you subject it to a process called hydrogenation. So you're actually exposing it to hydrogen, which saturates the double bond. But what happens in the process is that the double bond can actually flip. And so it can flip from a cis to a trans configuration. And why is that bad? Well, this is chemically what happens. So a cis double bond is the way we normally have it in nature. And basically what it means is that we have, it produces a kink in the fatty acid, which is important in terms of membrane fluidity. Remember, these fatty acids end up in a whole bunch of lipids, including phospholipids in our cell membranes. We want those membrane phospholipids to be nice and flexible because you've got a lot of important proteins in the membrane, ion channels, receptors, etc. So you want that degree of flexibility rather than freezing those proteins in by having saturated fatty acids. And a trans fatty acid produces basically a straight chain like a saturated fatty acid. And there's a little bit of dispute in the literature whether they're as bad as saturated fatty acids or even worse. So that's trans fatty acids. Now we're polyunsaturated fatty acids. So I'm sure you've all heard of this. And these are the ones which are considered essential because why do you think they're essential? Why do you think? You can only get them in diet, but because we can't make it ourselves. That's the critical thing. We can't make it ourselves. And so that's why they're essential. And so there's two families of polyunsaturated fatty acids, the N6 and the N3 family, also called the omega-6 and the omega-3. And you would have heard of omega-3 before. Is that something that you've come across time and time again? So, and we can't convert between these two families. Now, what does this nomenclature actually mean? Well, I talked about a chemist would count the double bond from the functional group. A biochemist actually counts from the other end, and there's a good reason for that. It's because if you count from the end of the molecule, which is where the N-6 comes from, or the omega, last letter of the Greek alphabet, it's the end of the molecule, that you can actually follow a fatty acid which is converted into another fatty acid because this position doesn't change. So, for example, ultimately this will be converted into arachidonic acid, and yet this is still N-6, this double bond here. Here we've got linolenic acid, the first of the N3 or omega-3 fatty acids, and we can see that double bond is 3 carbons away from the end. Eventually that can be converted to docosahexaenoic acid, and again this double bond is still at the N3 position, or omega-3 position. So that's why we talk about that nomenclature. So these can be converted, these parent compounds can be converted to a whole bunch of other compounds. These can be very important in their own right. So where do you think arachidonic acid was first found? Spiders, of course. So arachidonic acid is the precursor for a bunch of compounds called eicosanoids. These are things like thromboxane, prostaglandin. So they're actually really important in terms of vascular reactivity, vasodilation, clotting, asthma. So one of the leukotrienes can actually trigger asthma. Childbirth, prostaglandins are, of course, can be important in childbirth as well. And so they're very important compounds. A lot of the anti-inflammatory, non-steroidal anti-inflammatory drugs actually work by inhibiting production of these compounds, things like aspirin. Here, the omega-3 fatty acids, we've got docosahexaenoic acid, which is 22 carbons in length, 6 double bonds, and it's rich in organs which at least half the population hold very dear. And you can actually mount an evolutionary argument for that it was search, or it was really those N3 fatty acids which enabled the very rapid expansion of the skull in our primitive ancestors. And the same argument has also been put forward for red meat, but I think the argument for omega-3 fatty acids is probably a little bit more convincing. So you probably remember these ads from Sam Neill, red meat, we were meant to eat it. The reason that we could actually draw things like this. And I thought, just to balance it, I've shown the vegetarian argument with Missy Higgins holding a very cute pig. But remember that we should still be vigilant for swine flu. Okay. So 60% of the brain is actually lipid. So next time somebody calls you a fathead, just realise it's a fact. And the major polyunsaturated fatty acid in the brain is this docosahexaenoic acid, this very long-chain polyunsaturated fatty acid. And the major source of that is fish. So it's been proposed that a fish diet was essential for the evolution of the human brain, and that our ancestors either lived coastally in southern Africa or around the Great Lakes of southern Africa. Well, more eastern Africa, actually. And this, of course, is used in marketing, so that it seems that you can't go down a supermarket aisle without tripping over something which is omega-3 enriched, whether it's milk, bread, eggs, or even fish. And so here we have Smart Choice, because it makes you smarter. And it's got delectable flavours like light Thai crumb, light lemon and dill crumb. My mouth is starting to water. If it gets too much, just mop it up. But the thing to note here is that this is whitefish, very lean. The major omega-3 fatty acids that you're actually getting from this are from the crumbing. So the oil that they've actually chosen to fry the crumbing in. And that is actually the alpha-linolenic acid, so the parent fatty acid. So they're then getting us to do the work, trying to convert it into the long-chain polyunsaturated fatty acids like DHA. And we do that very inefficiently. So it's not really the same as eating fish. or eating an oily fish like a mackerel, herring, or salmon, tuna. And here is, so you can actually buy DHA pills on the net, and they're really seen as an aid for gaming to get to that next level. And of course, the problem with fish is that, as you've heard, that I think it's projected that within the next generation we won't have any fish in the ocean. So we need to find other ways to get our omega-3 fatty acids. And so let's make some pigs which make their own omega-3 fatty acids through a genetic trick. So they actually take a gene from the roundworm, C. elegans, often used in basic research, which can actually convert N6 fatty acids to N3 fatty acids. And so what you end up with is this sort of fishy bacon. Okay, so lipid-soluble vitamins. So if you were now that you're armed with just a little lipid chemistry, hopefully you can look at these and actually say, yes, that looks like a lipidy sort of thing. It looks greasy. So just take a moment, have a look at these, and just think why they might be lipid soluble from a just a very basic chemical point of view. So we've got vitamin A here. This is all hydrocarbon. We've got a hydroxyl group there. That's the only hydroxyl group we've got. Vitamin D2. And again, there's a hydroxyl group down here. The rest of this is hydrocarbon. Does that remind you of anything that we've seen today? Why don't you do a little bit of reverse origami and try to join this back to this? What would it look like? Cholesterol? Yep. So vitamin D actually comes from cholesterol, well, not specifically cholesterol, but a precursor of cholesterol called 7-dehydrocholesterol, which we have in the skin. UV hits it and then can open it up and form vitamin D, which is why vitamin D has been called the sunshine vitamin. Here we've got vitamin E here, mostly hydrocarbon. There's an ether group there. And then we've got these two ketos hanging off vitamin K. So what I've done here is just sort of try to tabulate, try to summarise maybe some things that you might want to know about these lipid-soluble vitamins, what their other names are: retinol for A, cholecalciferol for D, tocopherol for E, menaquinones, phylloquinones for K. I've got the deficiency, night blindness. Night blindness is still a major health problem around the world, particularly in parts of Africa and the Indian subcontinent. So they've actually now engineered provitamin A, carotenes, into rice to have this sort of orangey rice to try to alleviate this in parts of India. So it can be formed from carotene. Do you think you would be worried about toxicity with any of these things? Which ones would you be worried about with toxicity? All of them? Do you worry a lot? Okay, all right. I wouldn't worry about all of them. I'd worry about a couple of them. I'd worry about A and D. I don't know about K. I should, but I don't. I haven't really heard of vitamin K toxicity. Vitamin E is relatively benign. And you know, there's been hundreds of thousands of people who have been tested with vitamin E supplementation because it was thought that that would cure heart disease. Unfortunately, it doesn't. Now, I must confess that this is I hadn't seen one of these before because I never get that sort of money. But apparently this is the old currency, but I haven't seen the new one either. So I didn't know whether this was the new one or the old one. I believe it is the old one. Does anybody rich here? I take donations. No. No, so anybody know who this is? What do you say? Oh, somebody said Ernest Shackleton. Okay, that's a bad thing to say. It's good in a way because you've got the right continent that he explored. Wrong nationality though. Why wouldn't an American be on our $100 note? No, so it's actually Douglas Mawson, who we should... no, what? Who? He won MasterChef on Sunday night. Sorry, he didn't. That was somebody else. But he should be known. So he was a professor of geology at Adelaide Uni, South Australia. And he did some incredible exploring of Antarctica. And in 1912, he led a party going across this ice sheet with two other guys. And the guy with the sled and the best dogs, so this sled had all the provisions, is going ahead of them and suddenly just disappeared from view. And plunged down this crevice, never to be seen again, with most of the provisions. And so they then were stuck with pretty much no food, a few scrawny, rather tough dogs to eat, which they then did. The dogs had been eating seal meat. Fish is a good source of vitamin A. Seal, which eats fish, is even better, particularly their liver. Dogs which eat the liver is even better. Humans which eat the dog, it's a food chain, isn't it? You know about food chains. So they were getting way too much vitamin A. So they had vitamin A toxicity. One of the problems that they had was that their vitamin A toxicity results in skin lesions. And so when they were taking all this swaddling off their feet, you're talking about, what is it, minus 30 degrees would be a balmy day. Yet they're taking off all their swaddling, feet would fall apart. So, it was pretty tough. So that's an example of vitamin A toxicity. Who can tell me what that is? Rickets. Excellent. Good. So, obviously the femur being the longest bones in the body. Is that correct? I'm not an anatomist. I believe that's correct. Bearing all this weight from the torso, bending when the bones are being softened. And you need vitamin D for good bone development. So rickets. Like this is obviously a very old photo, very cute haircut. We don't have nappies like this nowadays. So is there something we don't need to worry about, vitamin D deficiency? Is that something which is long gone? You'd expect it to be a problem in the industrial north of Britain during the Victorian age, but it's not a problem in Australia where we have beautiful sunshine. Is that fair to say? So do you know about vitamin D deficiency in Australia? It is a problem. It is a problem. So this is just something that I dug up just before the lecture from the Cancer Council of Australia, who obviously have got, they're very concerned about sun protection, but they realise that vitamin D deficiency is still an issue. And they're identifying people who might be at risk, naturally dark-skinned people, because the UV doesn't penetrate their skin as effectively. People who cover their skin for religious, cultural reasons, elderly who are housebound, babies and infants of vitamin D deficient mothers, and patients with osteoporosis. So in other words, there is vitamin D deficiency. I believe there's been a few articles over the last 6 years about women having pelvic fractures during childbirth because of vitamin D deficiency. Okay, and then we've got, so tocopherol, if you don't have enough your red blood cells don't survive as well, but it's not too disastrous. Vitamin K, which is needed for blood clotting, half of it we derive from gut bacteria, which is why it's common practice to give new babies an injection of vitamin K so that they've got a little bit of vitamin K in their system for blood clotting. Okay, so that was lipid-soluble vitamins. I thought I'd pose a question, and I've actually answered this during the course of this lecture. So this really sees whether you've been paying attention or not. So what's the difference between fats and oils? Why, and is our adipose tissue a fat or an oil? Okay, so does anybody want to answer the first question? Yep.
Fats is solid root temperature, whereas oils is liquid.
Yep. Excellent. Yep. So why? Double bonds. So which way would they go? So would an oil have more double bonds, or what's that? Yeah. So oils have more double bonds. Is our adipose tissue a fat or an oil? Some people are saying fat. Okay, hands up if you think it's a fat. Hands up if you think it's an oil. Hands up if you don't care. All right, okay, good. Oh, that's brave. You're sitting in the front row. Very close, yeah. Yeah, this laser guided pointer, be careful. It's a trick question because it really depends upon whether you're living or dead. Because if you're living, you should be around 37 degrees, and it will be more like an oil. And yeah, like this is a little bit of a rubbery, contentious issue. But if you think about it, if it's actually a solid fat, you wouldn't be able to mobilise it. It wouldn't actually be able to jiggle. And just experiment, either with yourself or with your neighbour, but do ask them first and get 3 witnesses to sign consent. It does jiggle. It jiggles a bit more like an oil than a fat. If you're dead, then it will probably turn more into a fat. It will actually solidify a bit more. So, what's the difference and why? Well, as was expertly pointed out, fats are solid room temperature, like this lard here. Oils, like olive oil, are liquid. And that's because the melting point is lower in oils due to unsaturated fatty acids and triglyceride, making it a liquid at room temperature. And people used to actually eat this stuff. There's an ad for lard. They're happy because they eat lard. They were simpler times. Okay, so digestion and absorption, and I'm trying to work out how much I'm going to get through with this. So either we could have 5 minutes or we could have 15 minutes, but then in the next lecture we'd have to have 65 minutes. Okay, so we'll go for the 15 minutes more. Good. Okay, I'm glad we all agreed on that. Okay, so this is a very simple experiment. And we were actually thinking of devising this as a prac for you guys because it's cheap. And you can do this in the safety of your own kitchen, but do have parental guidance, please. So you can take water and oil, mix them together. What's going to happen? I just heard bleh. Maybe a representative from the first row. What's going to happen? Or what was the question? Don't you sit up the front so you can pay attention? Obviously not. No. Okay. Oil floats. So how many phases could we have? How many phases? How many phases? Yeah. Like, are they going to mix? No. So they're not going to mix and the oil's going to be on top. Yeah? Is that clear? Why? Why is the oil going to be on top? Lower density. It's less dense. That's going to be very important when we consider lipoproteins in the next lecture. So oil and water don't mix. Okay, what if you now throw in some detergent? So you borrow the detergent. You probably never washed dishes in your life. Okay. Detergent is something that you can use to wash dishes. So if you squat that in the top, mix it up, what's going to happen? Well, the answer's actually given up here. You just get one phase, and it's called an emulsion. So does that all make sense? If you understand that concept, you pretty much understand fat digestion and absorption. So what we're going to do is flick through. Sorry. Okay, I'm sorry. I don't know how that got in. Okay, so we're going to race through this pretty quickly. So digestion of fat begins in the mouth, and lipases are what causes the digestion of fat. Lipases, because they act on lipids. That all makes sense? So the first one is lingual lipase. Lingual, tongue, linguist. You can imagine a few words with lingual. So lingual lipase begins in the mouth. Continues in the stomach. Gastric lipase makes sense. However, adults really don't do a lot of that. It's only really milk drinking infants who do quite a bit of digestion there, because the fat in milk tends to be shorter chain fatty acids than the fatty acids that we generally consume, and they're very susceptible to action from these lipases here. Most of the digestion and absorption that we have takes place in the small intestine. So in the small intestine, we actually produce our own version of that detergent called bile acids. And so if you think about it, you're munching a greasy hamburger, you've got mechanical action, it's finally ending up in your stomach, and all that grease separates and basically is floating on the top. So how are you actually going to absorb it when it's just like an oil slick, like Gulf of Mexico? It's awful. What you need is you need to emulsify it, and you emulsify it with bile acids. So the bile acids solubilize the fats so that an enzyme, another lipase, secreted from the pancreas, pancreatic lipase, can split the triglyceride into free fatty acids and monoglycerides. So here we've got our triglyceride here. Pancreatic lipase is chopping this up so that we've got a monoglyceride just with one fatty acid, and then free fatty acids as well. Now, bile acids are actually made from cholesterol. They're synthesized in the liver from cholesterol. They're then secreted into the gallbladder and finally into the small intestine, where lipid digestion and absorption take place. And this is the structure of a bile acid. And hopefully what you can notice is that we've got a few more polar groups here. And so it's amphipathic, which is perfect for a detergent. You want it to have both hydrophilic and hydrophobic properties. And that's what the bile acid does. And so here we've got an idealized view. The triglyceride is shown as these golden tridents here. The bile acid's a nice bilious green. And here is the lipase as these sort of red blobs here. And so the bile acids are coming in, making the triglyceride accessible to the enzyme. What we then do is that just through the hydrophobicity of these lipids being produced, the monoglycerides and the free fatty acids, they form micelles, which just means that the fatty acids are pointing in, they're hydrophobic, water-fearing. The polar groups are on the surface in contact with water, so that's formed spontaneously. they're then transported across the mucous membrane of the belly into mucosal cells, also called enterocytes. And so here we've got the belly of the small intestine and these enterocytes on the mucosal cells here. Obviously, they increase surface area for efficient absorption. And so this summarises it: bile acid secretion from the gallbladder emulsifies the fat. The lipase secreted from the pancreas causes lipolysis, breakdown of the fat, micelle formation, uptake by the enterocytes. And this can be stimulated by gut hormones, for example, cholecystokinin. Now, I want to quickly, just in the last 5 minutes, talk about a couple of examples where fat absorption is impaired. The first of these is Xenical or Orlistat. Have you heard of this? So I believe it is actually still available over the counter at chemists. And there was an ad campaign a few years ago, which you might have caught, where they actually showed two drawings of a tummy, a chubby tummy, with this big sort of lipidy stain on it. And then after the Orlistat, we've got all of this lipid. It can't actually get in and make the tummy chubby. But it's not really a carefully controlled experiment, because if you look very closely, and you can't really see it in this light, but this is a paper towel, you know, the type that they advertise on MasterChef, extra absorbent, whereas this is sort of classical A4 paper, so it's not a fair comparison. But the more important point is that really it's an inhibitor of pancreatic lipase used in conjunction with a reduced calorie diet, reduces the absorption of fat-soluble vitamins and beta-carotene. And if you look at one of the earlier studies, over a year, it's decreasing weight just by a few percent compared to the placebo. Remember, these people are on a calorie-restricted diet, so they're losing weight anyway. It's only adding a couple of percent. So it's hardly the biggest loser territory of 50 kilograms in a week. So in other words, you pay a lot of money for perhaps a little bit of benefit. Just as an aside, this was actually developed by Roche, first as a cholesterol lowering agent. But then the statins came on the market. I'll talk about the statins in my third lecture to you. And that left the cholesterol lowering effect of these for dead. So they then tried to find another use for it. And this is what they did. As you can imagine, if you're not absorbing the fat, it's the alimentary system is relatively basic. Basic plumbing, you've got an inlet and an outlet. It's going out the outlet here, steatorrhea, oily stools. And this was an Australian doctor when it was first sort of reaching the market, which I thought was a rather paternalistic view myself. If a high-fat intake inadvertently occurs, the drug acts both to reduce fat absorption and educate patients with regard to hidden dietary fats. In other words, if a patient has eaten one too many donuts, Krispy Kreme donuts, they'll certainly know about it. Okay, so you know that potato chips are usually very fatty, usually 40% fat. However, in some countries, in America when I was there, they had this fat substitute called olestra. And it's basically got fatty acids esterified to sucrose. And what this means is that the pancreatic lipase can't actually get in to clip those fatty acids off. Not like a triglyceride. So it's what we call steric hindrance. So the olestra's chemical configuration is too crowded so that the pancreatic lipase can't get in to hydrolyze the ester linkages. As you can imagine, it has the same sorts of effects. In America, you needed to have this warning label on everything. And so olestra may cause abdominal cramping and loose stools. Olestra inhibits the absorption of some vitamins and other nutrients. Vitamins A, D and E have been added. But enjoy your chips anyway. And I think that's pretty much all we've got time for. In the next lecture, we'll talk about how lipids are transported around the body.
Those long shirts are awesome.
Couple weeks. Haven't had any fun.
Whoa.
Let's say something. Say something.